Okay, so we're going to look at scheduling. We're going to be focusing in on what the purpose of scheduling is and the scheduling algorithms that you need to know. So we're going to be looking at the purpose of scheduling, look at some ideas which go with scheduling, which are starvation and deadlock. We'll look at this idea that process can be in 3 different states, and also look at the following scheduling algorithms: first come, first served, round robin, shortest job first, shortest remaining time, and multi-level feedback. So it's important to be really clear about what we mean by scheduling. So on your computer system, you will have a large number of processes running at any given time. Some of them be fairly obvious to you, so these programs you physically opened up yourself, but also there'll be some that run in the background, which might be updating programs, it might be operating system, utilities, etc., etc. So because there's so many processes running, we need multitasking. As you know, multitasking is where we swap in and out processes into the CPU to give the illusion that multiple processes are running at the same time, when actually the CPU is just simply running them serially and the operating system is swapping them in and out. So the mechanism behind multitasking, where it decides, okay, this is the next process that needs to be run, we call scheduling. Okay, scheduling is all about the decision on which process will run next. Okay, so this is always managed by the operating system. It's not managed by the CPU at all. All the CPU will do is do what the operating system has instructed. So in order to understand scheduling, we've got to understand the states that a process can be in. Okay, so though not explicit on the spec, it is really important to understand what these states mean. So at any given time, if I've got a single core CPU, I can only have one process running. Okay, so regardless of what's happening, I can only have one running at any given time. We'll then have another state called ready to run. Now, all the processes that are waiting for CPU time will be in this other state called ready to run. And that's going to be stored in a queue. So there's going to be a queue date structure, and each process is going to be stored within that's waiting for CPU time. Okay, so there could be n number of processes. Now, although we call this a queue, it is really dependent on the scheduling algorithm that's being used. So it might be treated like a pure queue, or actually it might be played around with a little bit depending on the scheduling algorithm we're using. But we've got a third state called blocked. Now, block's really important to understand because it really helps with the maintenance of the system. So if I'm waiting for a device, let's say a hard drive, we already know, due to the speed mismatch problem and the von Neumann bottleneck, that hard drives are much slower than CPU. So if I had a process that's waiting for the CPU to finish saving or whatever, then it can't do much. It's waiting for a resource to finish. And because we know it's going to be slow, there's absolutely 0 point putting it into the ready to run queue, because if it was in there, it might end up going running and it will just swap straight back out again. Now that might not seem a big deal, but any swap between running and ready to run takes time. Okay, there's an admin cost, and because there's an admin cost, we want to limit the number of swaps that we can. So we put states that are waiting for a resource, such as a hard drive or a print or any other slow resource, into a block state. When an interrupt occurs to say actually this has finished, we can then move it back into the ready to run queue. So as you can see, we have a number of arrows pointing to and from the different states. So a new process always goes into ready to run. It's waiting for the CPU. It can swap between running and ready to run, and that decision is made by the OS. But if it becomes blocked, it might go from running into the blocked state, and it can only go from blocked back to ready to run. It can't just simply go back to running. When we are running, we might end up ending the process. Maybe you've closed it, whatever happens. So just a kind of summary: running, the process is currently running on the CPU, and we can only have one of those. Ready to run, process is currently waiting for process time, and that's going to be held in a queue. And blocked, process which can't continue because it's waiting for something to happen or an interrupt to occur. The ready to run queue is really important because this is where we're going to be getting the order of our things. So the scheduler is responsible for maintaining this queue. Okay, and that's really the fundamental reason behind it. So every process waiting goes into this queue, and in this example I've abbreviated all my processes to be P1, P2 rather than process 1, just to give you an example. And I've also given each of them time. Now, one thing that's really important to realise is that processes will need a certain amount of time to run. Okay, it might be that it needs to finish off whatever it's doing. It might be it needs to respond to an interrupt. It doesn't really matter what the reason is. The important thing is that it needs a certain amount of time. We measure that in milliseconds for this example, just because it kind of fits into our experiences. And it's simply an estimate, okay? It's not going to be the exact time, so I'm not saying it's going to take 10 milliseconds. It might take 12, it might take 9, okay? It's just a little guess. It just helps the scheduler to make decisions. So what is the purpose of scheduling? Well, we want to maximize the throughput of processes. That means we want to get as many processes through in a given time. Okay, so we want to make sure each process has a chance to run in a given amount of time. We want to make sure the CPU is being utilized as much as possible. As we know, because of the von Neumann bottleneck, we might have situations where the CPU is idle, and we want to minimize that as much as possible. We want to minimize starvation and deadlock, and I'm going to come on to what those terms mean in a moment. We want to ensure fairness. Now, fairness in this scenario is every process has a chance to run as equal to one another. We want to be responsive. Now, what I mean by responsive is that when I click on something as a user, something will happen in a reasonable amount of time. I'm sure you've had the click fury of something not opening, so you click on it 20 times and all of a sudden 20 things open up. So though that is really annoying for a user, so we want to minimize that by improving the response time, and we call that improving response, the responsiveness of the system. We want priorities because some processes need high priorities. That might be operating system stuff, and we want to use these slow devices, input output devices, and our slow resources as efficiently as possible. So let's actually consider a more of a real life problem. So we've got a bridge. And it's only wide enough for one car. I'm sure you've seen these bridges, probably normally in countrysides, but they do exist elsewhere. So it's common for two cars coming in different directions to meet in the middle. Okay, so that's not a good thing because they can't get past each other. So we don't want that situation to happen. So what is the worst case scenario for this? I've kind of just suggested already, and this is where I have two cars which are coming at each other at the same time. And imagine then cars were behind it. Now in this scenario, these cars can't go forwards, and it can't go back. This car can't go forward, it can't go backwards. Okay, it's stuck. We call that deadlock. Okay, so we're in a situation where no one can proceed. Okay, we're both completely and utterly stuck. So deadlock is when items are waiting for a resource that are never going to become free. Okay. In more practical terms, it's when I want two resources. Okay, so I've got process 1 and process 2. And I've got two resources. Okay, process 1 needs both of them, and process 2 needs one of them, both of them. So process 1 has resource 1, process 2 has resource 2. Now process 1 needs both of them to finish. Process 2 needs both of them to finish, but they've already got access to one of them. Okay, because process 1 doesn't want to relinquish resource 1, and process 2 doesn't want to relinquish resource 2, they're in a situation where neither of them can proceed, and that's deadlock. Another problem is something called starvation. Imagine we've got the same scenario of a bridge and I've got a car waiting, okay? It can see a car coming. So you think, you know what, I'm not going to go down there because if I go down there, I'm going to get stuck. The other car can't go forward. I'm going to be a nice driver. I'm going to let everybody think. So the cars come past and they keep coming, okay? You're stuck. You can't get past until the bridge is clear, but you have to keep waiting and waiting and waiting and waiting. And we call this starvation, where you don't get to use a resource, okay? You're waiting for it, but it's always being used by other people, okay? So, in this scenario, we come back to our bridge example. So we know what the worst case scenario. We need to find a fair solution to this. Okay, we need to find a way of avoiding starvation and deadlock. And how can we make this as efficient as possible? So what ways can we maybe do this? Okay, so have a think, and now we're going to have a look at the answer. So it might be a good point to pause and have a think before I give you the answer. So the most obvious way of doing it is a traffic light system, okay? But this is not actually a really good system. It makes sense to have a traffic lights. I'm sure you've seen them. So having a simple time on the traffic lights makes sense. So, when it's green, cars can go past, and when it's red, they're not allowed to go past. The problem is, what happens if it's green and no cars are waiting? Okay, we have a situation where that resource is not being used efficiently. There might be cars waiting the other way, but because it's red, they can't go, and there's no cars wanting to come the other way, but it's green. So we have a situation where the resource is not being used. So we need to find a way of solving that, having it as efficient as possible. And that, in a nutshell, is really what the scheduler is trying to achieve. Okay, it's trying to make sure that we don't have starvation and deadlock, that we're using the CPU as efficiently as possible, we're trying to use these slow resources as efficiently as possible, so essentially trying to get everything working as smoothly as possible. So in the traffic light example, it might be that it has a detector or a sensor which detects if cars are waiting or not, and you can see there's ways of maybe improving the scenario so it's made the bridge more efficient. So let's come back to summarising the purpose of scheduling before we go on to the algorithms. So we want to maximise the throughput of the processes, ensuring as many processes through in a given time. We want to maximise the use of CPU, ensuring that we're not waiting for slow devices, block devices, if there's something else we can do. So if I'm waiting for a hard drive to finish saving, I can go off and do something else which makes better use of the CPU. We want to get rid of starvation, want to minimize it so every process has a chance to run to completion. We want to make sure it's fair, so no, some processes aren't marginalized and ergo creates starvation. We want to be responsive to the end user, so the end user doesn't have to wait for things to happen. We want priority, so certain processes which are more important get to run first, and we want to make best use of any kind of slow resource. So it's time to pause and do a little task. So it's really important that you get the purpose of scheduling into your notes, talk about the role of the relative run queue, explain the different states the process could be in. Okay, although it's not explicit on the spec about the diagram, I think it's useful to give you kind of a bit of a background and grounding in what we're talking about, especially when it's talking about blocked. And here's an exam question to have a go at. Describe the purpose of scheduling. This certainly used to be a firm favourite. It could well be one that will come up in the future in some guys. And when you answer this question, I've got a little word cloud for you. So process, starvation, fairness, priorities, and throughput. So try and use these words when answering this question. So let's start looking at some of the scheduling algorithms, and we're going to use a special model where we number our processes, and each process has an amount of time that it needs to run for. And the process will run until one of the following happens. So we close the process. So the process finishes, it doesn't need any more process time, so it goes. The scheduler stops the process for whatever reason, and we call that preempting. The process gives up the CPU voluntarily, so processes can actually say, actually someone else can have a go at the CPU now, and pause. Or the process blocks, so it's waiting for some form of resource, and it moves into that block state. So the first algorithm we're going to look at is really simple. It's called first come, first serve. And each process runs as long as it wants to in the order it arrives. So it just simply works at a very, very simple queue. So we're not messing around with the rated run queue in any way, shape or form. We simply run it. We can still have a process which stops itself. We still have a process which blocks, but we're not necessarily going to preempt it. It's not very good algorithm, as you probably imagine. We have an issue with response time. So consider process 6 is a user interaction. So I've clicked on a button on an app, let's say, or I press a key on the word processor. In order for that to be processed, I have to wait until all the other process has finished. In this case, 196 milliseconds. Now that might not seem a long time, but it's noticeable by the user. And specifically, if we have more and more processes and need longer and longer to take, that kind of delay between me pressing the key on the keyboard or pressing the button on using my mouse will become noticeable. I am sure at some point in your computing career, you've been typing in words and nothing is appearing, and all of a sudden, all your letters appear. Okay, it's very annoying when it happens. It's very hard to type when you can't see what you're typing. And that's kind of what's happened behind the scenes. You know, it's the scheduler isn't scheduling the process which is dealing with your keyboard inputs. So the more processes running, the bigger the problem becomes for first come first. So let's have a little pause. What do you think the problems are with first come first served, and what are the benefits of it? So here's a list of our priorities, the purpose of the scheduler. So have a think about it. What do you think the benefits and drawbacks of first come first served are? So to summarise them, it's really simple to implement with a queue data structure. It's possibly the most simple scheduling algorithm out there. So it works well with processes we need short amounts of CPU time, so we don't have longer processes at all, we just have lots and lots of short ones, and that makes it really fair because they will just run in the order that they arrived in. Longer processes might monopolise the CPU. That's a big disadvantage. So if I have large processes which are ahead of shorter ones in the queue, then those short ones are going to take longer to get through. So it's not maximising the throughput, although I'm going to be using the CPU as per normal. It is going to get through as many processes as it can in the same amount of time. We might experience a lack of responsiveness as a result of some of these longer processes monopolising the time, and we're not going to prioritise these block processes, and as a result, some of the slower resources might not be utilised as best as they could be. The next one we're looking at is called round robin. Now, in round robin, we run it as first come first serve, but instead of just simply running it to completion, we're going to run it for a fixed amount of time. Now that fixed amount of time is going to be dependent on the operating system, so the operating system will make a decision, but that fixed time then remains the same and constant for the whole thing. So if I then preempt a process, i.e. I stop it because it's had its time allocation, it gets returned to the back of the queue. So let's consider an example. So at the top, I've got a simple kind of first come first served as it's running as before. And let's say I'm running 10 millisecond slices. So process 1 needs 10 milliseconds, so it's going to complete, happy days, no problem. Okay, that finishes as per normal. But process 2 needs 14 milliseconds, so it runs for 10, but it still then needs 4 left over, so it gets added back to the end of the queue, as you can see here. Process 3 is a longer process, so normally that would monopolise the CPU if this was just first come first serve, but in this case it's only going to run for 10 milliseconds, so then it gets added to the back end. So again, let's evaluate it. So what are the pros and cons of round robin? So have a consider of that. So it's implements with the queue. It's just ever so slightly more complex than first come first served. Improves the throughput processes because in a given time I'm going to get X amount of processes through. So it's going to improve the throughputs. It's fair because we've still got that first come first served situation. But it doesn't work well if I have lots of processes running on the system. So if I have 100 or 200 processes, then each one of those will have to run before it gets back to the first one. So the user might, as a result of that, experience a lack of responsiveness if there's a large number of processes running. And in a modern computer, there normally is. It's not prioritising those block processes. Again, we might have a problem with utilisation of our resources. And when we swap a process, I've already mentioned this already, it has a little admin cost. It's not an instant thing. It does take a little while to do. And as a result of that, the more I swap, the more time I spend doing admin, the less time spent running processes, ergo not utilising the CPU as efficiently as I should be. So now's a good time to pause and actually get some notes on these two algorithms. So make sure you write down how these algorithms work. It's probably worth putting a little example in your notes so you can can see it. Define what's meant by preempting, okay, because that word is really important. Ensure you include those advantages and disadvantages as well, because those are part of the spec. Describe the differences and similarities between the two, and that could be potentially a question that you could get asked. When you're describing the algorithms, make sure you are explaining exactly how they work. Don't just try and give a vague overview, because you could be asked the question and describe the round robin algorithm and you'll be expected to give the details. So for example, it holds process in a first come first serve queue. Each process is run for a set amount of time. When that process if that process doesn't finish, it gets added to the back of the queue. This then continues until all processes are run. So you can see there's a bit of detail in there. You need to make sure you get all of that. I've added a little word cloud as well to help you with the last question. So let's look at shortest job first and shortest remaining time. So we've got two algorithms which are very similar to one another. So I'm going to explain for shortest job first, and then I'll explain what the differences between shortest job and shortest remaining time are. So same situation as before. So here I've got my first come first served queue as per normal. Shortest job first, instead of just running it in the order it arrives, it actually rearranges the thing. So it creates what's called a priority queue. In a priority queue, the shorter processes will go first and the long processes go at the end. So the second one here is essentially me reordering it based on time. So the shorter processes come first, the longer processes go at the end. New processes, and only new processes, are inserted in the queue based on that time order. So when a process is preempted, it gets added to the back of the queue as per normal. Now, you're probably thinking, well, okay, well, that's all going well, but why do that? What's the rationale behind it? And in order to explain the rationale, I need to just kind of give you a little indication of the nature of some processes. So there's two common activities which processes perform, which only require a very small amount of CPU time. One is accessing any kind of slow resource or device, so i.e. coming in and out of blocked. Those only need a short amount of time, because what will happen is it will send some data over to the device or receive some data from the device, and then it will block again, or very likely. So if I'm saving a Word document, for example, it will save a bit of it, block, save a bit more, block, save a bit more, block, and it just needs a little bit of time to actually go from blocked to unblocked, send the data again, right, block again. Okay, so there's only needs a short amount of time. User interface operation, so pressing the key on the keyboard, it's not computationally very expensive, doesn't take long to do, so those tend to be very short processes as well. Because of the nature of these two as well, because they are short, they both need to be handled very quickly. Okay, so if I don't handle a block process quickly, then it's going to not use the resource efficiently. So because those resources are slow, I want to try and use them as efficiently as possible and optimally as possible. User interfaces, if there's a delay in responding to user interface interactions, then the system will seem unresponsive, and that's obviously annoying for the end user. So we must prioritize these two types of actions. So can you see any problems with shortest job first, and can you see any benefits to it? So advantage of shortest job first, because these user interface operations and blocked operations only need a small amount of time, it prioritizes them. So it prioritizes those slow resources, it prioritizes user interface interactions. That's going to make things feel more responsive. And it will improve the throughput process. We're going to get all the short processes through, which means that we're going to get more processes done in the same amount of time. But it's got one really big problem, and that's if I do happen to have a larger process, or a longer process, should I say, that may well suffer from starvation. Okay, give you an example. imagine you're waiting in a queue to get some food, and you're letting the year 7s in every time. So every time you see year 7s in, okay, in you go, you can go before me. And in that scenario, you might have loads and loads of year 7s keep coming in, you never get to the front of the queue. So it's not as fair as other scheduling algorithms as a result of that. There is another one which is similar, which is called shortest remaining time. The big difference here is that when the process is preempted, i.e. I stop, the operating system stops it, it gets inserted back in the queue based on the amount of time it has remaining. Okay, so shortest job first only does it once, while shortest remaining time does it every time it gets reinserted back into the queue. So can you see drawbacks or benefits of shortest remaining time, especially compared to shortest job first? So again, it's prioritising those user interface and block processes. It improves the throughput of processes, and also longer processes will increase their priority over time, and that's one of the key differences between it. So let's say a longer process gets a little bit of time, gets preempted, because it needs less time next time, it's going to have a slightly higher priority. Okay, it's going to have a fewer processes going in front of it, and over time that priority will increase until it finishes off. It may still suffer from starvation, but the problem is mitigated a little bit, and it still suffers from a lack of fairness. So do make some notes on it. Focus on the similarities and differences between shortest job first and shortest remaining time, and make sure you include the advantages and disadvantages of them. The last algorithm we're going to be looking at is multi-level feedback queues, and this one is very different to the others. So instead of having just one ready to run queue, I end up having 3. Okay, that's where the multi-level comes into it. Each queue is first come first served as per normal, and we always run processes from level 0 first. Now, in order to manage the multi-level feedback queues, we have a set of rules which we follow. So if a process is preempted, then we demote it by 1 level. So if the operating system says, okay, you've had enough time, I'm preempting you, it will go to 1 level below and join the back of the queue. If it happens again, obviously, it's going to go to the bottom queue, and obviously there will remain. So it's essentially stopping a longer process from monopolising the time. Because remember, with first come first serve, we had the problem that longer processes may monopolise the time. This kind of fixes that problem. But we also have an issue with starvation, okay? Because if that's going to be demoted every time, it could be starved of CPU time. However, we've got a kind of a way of getting out of it. So if a process gives up the CPU time voluntarily, then it stays the same level. So we've got a kind of a difference here. Preempted means the operating system is stopping it from running. Giving up CPU voluntarily means the process has made a conscious choice to say, okay, someone else can have a go. So we're going to reward that behaviour to say we call it a well-behaved process. So longer processes, because they can monopolise time, if we program it in such a way that it always periodically gives up CPU time to let another process run, that it's going to be more responsive. It may take a little bit longer to finish, but it's going to be more responsive, which ultimately is better. So we reward that kind of behaviour, and we punish, for want of another word, processes which are forced to be preempted. If a process blocks, then we promote it. Now, the reason we do that one is because we want to really prioritise any access to slow resources. So any block process gets promoted because it's going to be dealing with the slow resources. We want to make sure that is run as soon as possible. And new processes will always start at level 0. So, final evaluation. Can you see any problems or benefits of multi-level feedback queues? The advantages: prioritises process using slower computer resources by promoting them. Prioritises GUI operations because they always start at level 0 because they're going to be short, they're just going to go straight through. Improves the throughput of processes because any process which is poorly behaved is going to get demoted. And encourages good programming practice because if I don't program my longer processes, well, then they're going to take longer to run as a result of that. Disadvantages: longer, poorly coded processes are going to suffer from starvation. However, one might say actually that's probably a good thing. So, notes task, to explain how they work and describe why multi-level feedback queue meet the requirements of the scheduler for the OS. Okay, and I've listed what those are on the slide. So just to finish off, here's the subject clarification. So candidates need to understand the need for the scheduling of tasks, so that's the purpose behind it, of the operating system and the benefits that scheduling brings. Okay, so that's the benefits of multitasking. Candidates need to understand that there are different scheduling algorithms, so you need to know all those different algorithms, what their benefits and drawbacks are for those tasks with specific characteristics. When it says specific characteristics, it's talking about blocked processing waiting for hardware, it's talking about user interface ones, it's talking about those longer processes may need more processing time, etc. Candidates need to understand how the following scheduling algorithms work, so it's listing them out there. So you need to know what they are, their benefits and drawbacks, and the kind of tasks that they work well with.